Welcome back, Level 1 NCEA physicists and earth scientists, continuing on with the electrical energy portion of the energy external, today looking at voltage. So the way I look at voltage is similar to mechanical energy. So here we have an aircraft travelling at say 30,000 feet. It has an initial gravitational potential energy, and then as it lands on the tarmac, it's going to have a final gravitational potential energy. And the difference in the gravitational potential energy is going to be the potential difference. So this is similar to a circuit where it's now electrical potential energy difference. So in the beginning, we have a cell. It's going to provide chemical potential energy, which is then transferred into electrical potential energy. As it moves around the circuit, it's going to hit a component, and then the electron is going to transfer its electrical potential energy into the bulb to create light energy. Okay, so it's going to transfer that, then go back to the cell to get more electrical potential energy. So electrical potential energy difference is also known as a volt, and 1 volt is equivalent to 1 joule of electrical potential energy per coulomb of charge. So in terms of measuring potential difference, we use something called a voltmeter, and it must be done in parallel as opposed to series for current in our previous lesson. So the reason why is you need to measure the electrical potential energy difference across a component. So the electrical potential energy going into the component, then the electrical potential energy coming out of the component, because it's the difference which is being transferred into another form of energy. So looking at, say, for example, a hurdler, because it's the Olympics. So this young lady starts with 60 joules of energy. It's then transferred when she jumps across a hurdle. That's 20 joules of energy is transferred into other forms. So she now has 40 joules of energy. Then again, she jumps across a second hurdle, and that's transferred into 20 joules of other forms of energy. And then again, 20 joules now she has left. And then finally, she jumps again, the final hurdle, and that is transferred into another 20 joules of different forms of energy. So now she has 0 joules at the end. And so you can see the potential difference as she jumps across each hurdle is 20 joules of energy being transferred into other forms. So this is very similar to a circuit. So the electron collects that's 1.5 joules per coulomb of electrical potential energy. Then it moves around, it hits the first lamp, it then gets that transferred, the electrical potential energy, into light energy, and then it now has 1 volt worth of electrical potential energy. Then it moves along to the next lamp. It then has again 0.5 volts of electrical potential energy transferred into light energy and heat energy if it's an efficient bulb. Then moves to the third one. It now basically transfers that final 0.5 volts of electrical potential energy and then has 0 volts at the end, goes back to the battery, collects more electrical potential energy, and the cycle begins again. So in summary, the potential difference of a component, or the voltage of a component, is a measure of how much energy is transferred in the component. Okay, so in the previous example, you'll have 1.5 joules being transferred per coulomb of charge into light energy, and the potential difference across the cell must equal the sum of the potential differences across the component in a series circuit. So for each of those lamps, remember it's you started off with 1.5 volts. Each of those lamps were 0.5 volts. 0.5 times 3 is 1.5, so it all adds up. And then, as I've mentioned, another name for this electrical potential difference is known as voltage, and it's the amount of energy per charge, or the joules per coulomb, and this is of course called the volt. So in terms of circuits, in a series circuit, which we've looked at, the current is the same at any point. We've learnt that yesterday in the last lesson. And the electrical potential difference is split over each component. Okay, and in parallel circuits, the current is split down each branch. Again, we learnt that in the previous lesson. And the potential difference, or the voltage, is the same across each branch.